Rohan will be presenting a talk titled "The Program to Find the Permutation Matrix that Shows if Two Graphs are Isomorphic from the Adjacency Matrices." So over to you, Rohan.
Thank you so much, Professor. Just give me a second, I should share my screen. All right. All right. Good afternoon, everyone, and welcome. My name is Rohan Mitra, and I'm currently a junior at the American University of Sharjah. I'm pursuing a double major in computer science and mathematics. So this talk actually is based on something that has linked both of my main passions, computer science and mathematics, into one project. This is a personal project, and I had written a program to help me solve a problem in graph theory. The program is actually to find the permutation matrix to show if two graphs are isomorphic. Now, it sounds very complicated, but in my talk, I'll make sure that it's very easy for you to understand this and use my program. Let me begin by giving a little background on how I came up with this. So I'm currently taking the course Math 418. It's called Graph Theory. I'm taking it with Dr. Ayman Badawi right now, and I'm really enjoying the course because graph theory has a lot of connections between mathematics and computer science. It connects both of my favorite things, and it really connects pure maths to computer science very well. Graph theory is usually a way to visualize different, more pure maths concepts, and relating it to computer science makes it practical. That's what I really like about this. Well, the way this program came to being was that I had homework, okay? Just like everyone, all the students attending here, I had some homework in graph theory. The question was to find if two graphs are isomorphic, and I had to show that they were or weren't. Now, that was a long process, and honestly, I had a tiring week. So something in me, the programmer in me, decided that it's time to find a faster way. Okay, I knew these questions are going to come up. It's the beginning of the semester. I knew these questions are going to come up again and again. I need to find a faster way to do it. And, well, what's faster than humans? Computers, isn't it? So I quickly opened up my coding environment, and I took about 10 minutes and coded a solution. And that's the program I'm actually going to present to you here today. I've had a fair experience in coding. I'm currently working as a research assistant for machine learning. And I also work a lot in competitive programming. In fact, I just finished a programming competition and just came. So this is why it took me a relatively short amount of time, although it is not that complicated if you know what you're doing. Okay. I had a couple of my classmates test it out. So some of my classmates who knew coding very well and who are taking this course with me, I asked them to test it out just to check that it's not only working for me, but it's a little more generalized. And once they confirmed it, I shared it with my professor, Dr. Ayman Badawi, who's, I believe, here with us today, and who shared it on iLearn to all my classmates who are taking graph theory. So they're able to use it and basically find a lot of different ideas and concepts relating to isomorphisms of graphs. Now, I said a lot of big words there, so let's just back up and take it slowly. Okay. So first, let's talk about what is a graph. Now, a lot of people, the first thing that comes to mind when they think of graphs is there's something on the x and y coordinates, and there's like y equal mx plus c, y equal x squared, something like that. But these kind of graphs aren't the classical graphs most people are familiar with. These kind of graphs are actually a set of vertices or nodes that are connected by edges, which are basically just connections between the nodes. So if you look at this diagram here, this is actually a graph. Each of the blue circles here are vertices or nodes. You can refer to them interchangeably. And edges are the connections between these nodes. Now, this looks a little abstract, so let me give you a little example. Think of this as the metro line in this country, right? Each node, so each blue circle, is a stop. It's a station you can get in, get off. And each black edge is basically the route between stations. That's where the metro will be traveling. Another way, for some of you who are familiar with computer networks, you could think of these as routers and connections between the routers or switches. So this is why I really love graph theory, honestly. You can apply it to so many different things. You could think of these as cities, and you can drive between these cities, right? So all of them would be valid ideas to how you can apply a graph. Now let's talk about isomorphism. It's a complicated word, but it's actually not that bad. And honestly, even I was a little apprehensive the first time I saw it. Basically, isomorphism is when you have the same graph, you just draw it differently, right? So if you take a look at the example here, you have G1 and G2. Notice I can clearly say G1 and G2 are isomorphic because obviously I just moved up the node number 4. I just moved it up a little bit. You can see it right here. And node number 5 and 6 have just been moved to the side. They've been moved a little lower. So clearly it's the same graph. I just drew it a little differently. I just moved the nodes a little bit up and down, right? Now the good thing about isomorphism is that both the graphs will have the same properties. Now I'm not going to get into all the details of the properties, but by definition of isomorphism, graphs have to have the same properties if they're isomorphic. Okay. Now, clearly G1 and G2 are isomorphic. I just moved the node around. But now when I tell you, what about G1 and G3, this graph right here, suddenly it's much less obvious, isn't it? This is the kind of question I got in the homework, and I was puzzled for a minute or two. There's a lot of different ways you can try and think about how I got these two. I can tell you for sure that G1 and G2 are isomorphic. They are the same graph, I just drew them differently. But that's because of how I constructed them, right? But from visually, I'm pretty sure all of you would agree. There's no easy way for me to see that they're isomorphic. So that's when my program comes in. But right before we get to the program, I need to introduce one last concept. This concept is of the adjacency matrix. Now this seems a little unrelated, but I'll show you how it relates to our problem in a minute. First, let's understand what this is. Okay, it's basically a matrix, so it's like a table, you could say. It basically has each column and each row that corresponds to each vertex, right? So each column and each row would correspond to a single vertex on our graph. Now you would go through this matrix and you would put a 1 wherever there is an edge between any two vertices. If there's no edge, if there's no black line, you would put a 0. Fairly simple, isn't it? Let's try it out here. So let's take a look. We have row 1, and this is column 1. These two refer to the same vertex, 1. Now, if I go through, there is no black line between 1 to 1, is there? Well, clearly there isn't. So I put a 0. Between 1 and 2, there is a line between them. Yeah. So let's put a 1. Okay. Similarly, 1 and 3, there is a line between them, so we put a 1. Notice now 1, 4, 1, 5, 1, 6, there are no lines between them directly. Obviously, I could go from 1 to 4 by going via 3, but there's no direct line connecting any of them. So they're all zeros, right? Now that would continue for the entire matrix. Now you start with row number 2. So vertex 2 is connected to vertex 1. Yes, it is. So you put a 1. Vertex 2 connected to 2, and it is not. So you put a 0. And you can continue in this fashion, right? So adjacency matrices, honestly, I find it pretty fun to compute. And I also feel that it's very simple to compute. It's just such a simple rule, isn't it? You can just take the first column or row, whatever numbered row or column it is, just check if it corresponds to the other node. And if they're connected, put a 1, otherwise put a 0. Simple, isn't it? This is something I felt when I first saw this. The first thing I felt when I saw this was that, hey, this looks like a children's activity. Something on those lines, obviously a little more complicated, but it could be a children's activity, isn't it? If there's a line, write a 1 or color it blue, something like that, right? So this is why I preferred using the adjacency matrix in my program, because it's very simple to compute, right? There's nothing difficult to compute about an adjacency matrix. Just look at your graph, right? You could, in fact, you could probably write a program to compute the adjacency matrix if I give you a graph, right? That's possible too. I haven't done that, but I could probably extend my project to do the next thing. Now that we understand the adjacency matrix, I need to explain one more thing. A new definition of isomorphism, because now we know what an adjacency matrix is. So let's redefine isomorphism. Because first it was very visual. You could just see it and say yes or no. But it's not the way mathematicians do, right? So let's look at a more mathematical definition of isomorphism. I say that two graphs, G1 and G2, are isomorphic. That's what the approximate sign means. If and only if, for their adjacency matrices A1 and A2, they are the adjacency matrices for their respective graphs, I can find a matrix P such that P times A1 is equal to A2 times P. Note here we're using matrix multiplication, not something like the Sharjah product or anything. So it's P times A1 equal A2 times P, or, well, the vice versa. PA2 is equal to A1P. In fact, if you find either one of them, you could find the other one just by inverting P. There's also a bit of theory you could look into that determinant of P would actually never be 0, so it would always be invertible, because P is usually derived from the identity matrix. Although that's a little more theory than I want to get into at this point. Now, P doesn't have to be unique, but it is definitely fun to compute multiple values of P, and that's what my program can get you. It can get you multiple values of P, although any one of them could be used to show isomorphism. Okay, so let's consider these very simple graphs G1 and G2. Now, I'm very, very sure all of you would agree with me when I say that they're isomorphic. Come on, I just rotated it, right? I'm pretty sure all of you can see that. Now, I also relabeled the vertices, so it's a little more complicated than it might normally seem. So let's compute our adjacency matrices. I computed A1 and A2, the respective adjacency matrices. Notice, for example, node number 2 is on the second row, which means it has 3 connections to 1, 3, and 4. So 1, 3, and 4, and so on. Now, I computed this value of P. So if you were to try this out, and I encourage you to try it out, P times A1, and try to see if that's equal to A2 times P. Okay, but you know what? Rather than me believing me that I computed this value, let's compute it together. Let me go to my program. So here's my program, and I'm going to run it here on the side. Okay, so first notice it asked me to enter the value of n for an n by n matrix, right? So this matrix here, it was a 4 by 4 matrix, so I put a 4, right? Now I entered the matrix A1. For simplicity's sake, I didn't require them to put spaces, right? So that's the first row of A1, second row of A1, third row of A1, and the last row of A1. Then A2, note I'm just copying this from the slide. I'm not changing anything. It's exactly like you would have normally computed it. And the last row here, and I hit enter, and look at that. It found 2 values of P, both of which would give me an acceptable answer. And because it has found values of P, it's told me that, hey, A1 and A2 are isomorphic, and there are 2 such matrices that could be used as P. Perfect, isn't it? You can take a look here on my presentation. I've used this matrix with 1s on the second diagonal and a 1 here. Notice that is the first matrix. That's this value of P. It's the 1s on this diagonal and a 1 here. But note that there's also another possible value of P I could have used with different values in each column and row, right? So this is what my program essentially does. It's going to take in your adjacency matrices, going to find you the value of P, and by this theorem, by this new definition here, we can easily justify whether they're isomorphic or not, because if it's a bidirectional condition, it's an if and only if, right? Similarly, now we can look into trying a harder example. So I've made 3 more graphs, G1, G2, and G3. Now these are 6 by 6, and they're not so easy to see if they're isomorphic or not. So let's try this out with the program, okay? Let's go ahead. Let's first test if G1 and G2 are isomorphic. Then we'll try and test if G1 and G3 are isomorphic, okay? So let's try that out. So let's go ahead and try G1 and G2. Now notice there are 6 by 6 matrices, so I shall put the number 6 in here. Enter the matrix A1. Now this might take a minute, but I'll get done. Notice I'm entering these just as it was on the slide. Once again, no changes. And last one is that. Okay, the second matrix 0, 1, 0, 1, 1, 0. 1, 0, 1, 0, 0, 0, 0, 0, 1, yeah, okay. 0, 1, 0, 1, 1, 0, okay. 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, and 0, 1, 0, 1, 1, 0. And there we go. Now check it out. If you notice, the program gave a lot of output. All of these are values of P. Crazy, isn't it? So there's so many values of P, and clearly it's isomorphic because I found at least one value of P. All those values of P, it's incredible. So clearly A1 and A2 have to be isomorphic, right? By the theorem, by the definition, I found a P. In fact, I found 72 matrices that could be used as P. And that's the point of this program. Sometimes there's times that you might find a value of P that might be different from maybe what you've got. And this program can help find all the values of P. Moreover, I'm not entirely sure about what exact theorems, but I'm sure that there are theorems that rely on the number of matrices P that are available. And this could easily demonstrate that. Now let's take a look at G1 and G3. Let's test the isomorphism between G1 and G3. So once again, I'm going to input 6 and G1, 1 0, 1 0 0 1 0 1, 1 0 0 1 0 1, 0 1 1 0 1 0, 1 0 0 1 0 1, 0 1 1 0 1 0, and then the matrix A2, which will now be by third graphs matrix, right? 0 1 0 1 1 0, 1 0 1 0 0 1, 0 1 0 1 0 1. Okay, where was I? And it's 1 0 0 1 0 1, and the last row 0 1 1 0 1 0. Notice this. It says error, unable to compute such a matrix P. Please check if A1 and A2 and make sure they are correct, right? So there's obviously a scope that every program is only as good as the user's input, right? So I've asked the user that make sure that they are correct. If they are, then A1 is not isomorphic to A2 because I could not find such a matrix P such that PA2 is equal to A2P. The PA1 is equal to A2P, right? And that's exactly my program. That's exactly what it does, right? So you could clearly find out that G1 and G2 are isomorphic while G1 and G3 are not. Now, depending on how you want to view this, you could have gone either way if I generally asked you to stare at it and try. And that's the real point of this program as well, right? It's easier to find these values of P, how many values of P are possible, and if there are any values of P at all, right? Some final observations are that I've tested this program on multiple graphs, isomorphic and non-isomorphic. I found many values of P. Some graphs only have one value of P. That's one of my observations. Some have obviously 0. Now it can be used to simplify complicated graphs, right? So usually isomorphism is strongly used, and I learned this from my abstract algebra course, that isomorphism is strongly used to when you have something that is very complicated and not well known. You can show that that is isomorphic to something much more well known and whose properties we know. Now remember, I told you earlier that if they're isomorphic, the properties are exactly the same. So if you have something complicated, you can try and show that it's isomorphic to something well known, and you know everything about the complicated graph now. Now, based on this program, I'm going to do some further work to improve efficiency of the program. Keep in mind, I was recording this for my homework, and finally it's taken up to this step that my professor, Dr. Badawi, encouraged me to present here, and I'm really glad I did. So there are some places I've found for increase in efficiency of the program, which I will carry out next. And hopefully, if the efficiency is large enough, I could use it for further projects. This is one of my personal projects. I could use it for my senior project or something like that, to basically work with a large number of vertices quickly. That's the main point. Now, I also want to share my code. This code is open source, so even though I've coded, it's available for all of you. You can scan the QR code there on the left to find my code on GitHub. You could run it directly in your browser if you like, using the QR code on the right. Thank you all for listening, and that's the end of my talk. I'll be open to taking any questions now. Dr. Ayman, yes. Now I can add one more property to human graph structure. We showed the 72 different isomorphisms. I thought G2, G3 isomorphism. Yes, Dr. Ruichi, I thought the same originally until I actually ran the program, and it turns out they weren't. Yes. Okay, I like Dr. Badawi's point actually. that there are actually 72 different isomorphism functions. So the way these isomorphisms come is through finding a bijective function between two graphs' vertices. Now, obviously, that is a little more complicated than what my program is doing, but essentially it's the same thing. And as Dr. Badawi pointed out, since there are 72 different values of P, that indicates that there are 72 possible functions to map as a bijective map from G1 to G2. Thank you all.
You just run G2 and G3 in your program.
Okay, let's try G2 and G3.
Just for fun.
Okay, sure. Let me exit this. Let me exit this. Okay, let's try G2 and G3. Let's try. Where is it? Okay, run. It's a 6x6 matrix. Where is G2? 1 second. Let me. Okay, here. 1 0 1 1 0. Then 1 0 1 0 0 1. 0 1 0 1 1 0. 1 0 1 0 0 1. 1 0 1 0 0 1. 0 1 0 1 1 0. Now we have G3 0 1 0 1 1 0 1 0 1 0 0 1 0 1 0 1 0 1 1 0 1 0 1 0 1 0 0 1 0 1 and 0 1 1 0 1 0. They are not isomorphic. Now theoretically, there's an explanation for this, that since G1 and G2 are isomorphic and the isomorphism has a property of transitivity, since G1 and G2 are isomorphic and G1 is not isomorphic to G3, it's automatic that G2 cannot be isomorphic to G3 as well.
And so can you tell us a little bit about this P? How do you get it? What is this program? What does he do actually?
Okay, so this particular program actually, it tries out different values for P. If you noticed in our examples, the values of P were always a particular matrix that looked like the identity matrix, because each row and each column had only one 1. So there's a unique 1 in each row and each column, right? Rest all are always zeros. So what I did is I tried putting a 1 at each location here. So tried putting a 1 at this column and filled it in sort of like the game of Sudoku, where you just fill it in and make sure that there's no other, the same number is not available in the same row and column. So I put a 1 in each of these rows and columns and try out the different combinations available. When I try out these different combinations, every time I put a 1, let's say I put a 1 first in the first row, first column, then the second row, second column, third row, third column, etc., and get the identity matrix, I start with that. And then slowly I move each of the 1s around like you're playing Sudoku. You would try it out and see if it would work. And that's essentially what my program is doing. So it tries out all the different possibilities to place these 1s in a matrix and then does it. That's why it doesn't take too long. Even though it was a 6x6 matrix, it didn't take too long, maybe like less than half a second, because I don't test every single possibility. I test the possibilities where I require a 1, right? Wherever I need that 1. But I still found a single scope for improvement, which hopefully I will look into after this conference, and maybe I'll present next conference again. Or if you guys want to use this code here, you could see my updates on the QR code on the left. I keep updating it, and anyone who wants can keep accessing it right here. Hopefully, I found some place for increasing the efficiency, because while computing these, there are certain regions that I may not need to check. So I could try figuring out when I would not need to check separately. Well, otherwise, I check every 1 in different possible arrangements.
What are the limits of your program in terms of size? Did you try?
I haven't tried a very large matrix. I predict it to be maybe 100. That's my prediction. But then again, I haven't tried it out and done anything. Once again, it was just something I did to finish my homework quickly. But of course, I do feel like I want to try it out. I think I will generate 2 matrices that are isomorphic and non-isomorphic and try it out. I think I should, that's my next step in this program.
So you never tried for a huge matrices to see if it is fast, or if it's gonna take a long time to compute the P?
No, I haven't tried for huge matrices, although by algorithm theory, it should be about, I'm thinking about 100 and something. At least like in the hundreds somewhere. That should be the max, that it doesn't take too long. Maybe like a couple of seconds you could get in, like hundreds in a couple of seconds. Yeah, maybe a minute or two. That's what algorithmic theory says. But of course, I have to practice and try it out, and then I can confirm for sure. But theoretically, it should be in the hundreds, and in a couple of minutes, you'll get the answer.
Thank you.
Thank you.
Rohan, very nice, fascinating talk. I have one comment and one question.
Yes.
I like those QR codes that link you back to your GitHub codes, so I really like those.
Thank you.
QR codes. Another question is, have you applied your research or result to any real-life application?
Actually, no, I haven't. So some of the questions given in that homework with Dr. Badawi are actually linked to abstract algebra. So it's related to group theory in abstract algebra. So one way, when I mentioned that I tested this program on multiple graphs, I actually picked up some groups in abstract algebra that I knew were isomorphic or not, because I took abstract algebra last semester. So I know how groups work. So I just picked up groups, put them in graphs, and then tried it. So the current application that I could have done so far has been in abstract algebra.
Okay, that's really interesting. Something else you can look into or apply in real life application, your research and result, is that you can look at applying it to the blockchain and cryptocurrency network and determine fraudulent behaviors in the network. That's something quite hot at the moment, and there's quite a lot of researchers are looking into determine these fraudulent behaviors on the blockchain network and using your type of research and results. Yes, so something that you can look into.
I agree, sir. Thank you for your suggestion. I'll definitely look into it.
Yes. So yeah, once again, thank you very much, Rohan, for your presentation.
Thank you so much. It was my honor presenting here. And thank you to everyone in the chat.
So that is our last talk. And I would like to say thank you all again for all the presented participants today. Without your participation, as I said, this conference could not happen. Throughout this session, we have had a lot of fascinating spectrum of different mathematics talks within this session.